Good morning, everyone. I guess I should say boo, right? Halloween today, so hope you have a nice day and moving forward. Uh, I am working on exams. I'm about halfway through this class. I finished up Monday's class, got them posted, was trying last night, and I just couldn't see straight anymore, so I just stopped and hopefully get them finished up today. Uh, the good news, I guess, is that this class seems to be about on track to how the other class was performing. Actually, last time you did a little bit better, but there was about 70% of the class scored better on test 2 than on test 1, or better or the same. Um, and those who didn't score quite as well were just a little bit off, so it's good progress. Also, I heard from the coordinator, they sent us, there's two of them, they sent us a message saying that officially all classes will replace the lowest of the three test scores with how the final exam turns out, if your final is better. Okay, so do better on the final, it replace that. That's what we did last time, so I figured that was coming. However, I also still will look, and again, it's nice when I see good progress along the ways, because I can go sort of outside the scores of this is, even if the score isn't quite there, is the effort there. So with that in mind, I have opened up all previous homeworks until December 1st, so you can go back and finish up anything. As soon as you hit 80%, you get all the points and plus even the extra credit points. So at least get them to, if you get them to 80%, the more you do, of course, it could be helpful. Although there are some in the end that are more just, challenging and they won't necessarily help you do better on the test. So if they're a frustration, leave them, get to that 80% and say, I'm good, I'll keep moving forward. And the main thing is to keep on track, because where we're at now as we get to test 3 is, so today we're doing substitution, but you see basically 12.3 and 13.3 and 13.4 are similar. One is an algebraic look, one's a numerical look or graphical look at the same topic, which is what we're doing today. And then we've got one more section. So test 3 is going to be very narrowly focused on just what we're doing on integration. So it's a good chance to get a nice, strong score if you focus on this part. After we finish test 3, we have about 2 weeks to kind of finish everything up. And again, everything will be open, so there's no time constraint on you to hopefully make everything work. So if you can get most, or if not all, of the homework assignments to 80%, that's a good sign. You did all the work, you did what you could do to learn. And again, it's not just about getting it done, but also hopefully learning along the way. So that's a good indicator. And then show some improvement in the tests. And again, as long as you can pass the final, since the final is comprehensive, you will pass the class. Okay, I guarantee you that. Doesn't mean that some people will turn that around. If I fail the final, I'm going to fail the class. Not necessarily. If you've been doing well, you could actually fail the final and still pass the class and still actually maybe get a good grade, but you probably won't. If you've been doing well along, you will probably do just as well, because the questions, the tests are very much the same. Okay, so any questions before we head into our next topic? All right. And again, I think today's the last day to withdraw from the class, so some people have been contacting me. If you made it this far, I say just go. I've had a few not so pretty grades on my transcripts. When you retake the class, at least everywhere else I've been, the new grade will replace the old grade. You've already paid for the class, so my suggestion is just stick it out. You're going to need this class anyway, so it's better to do your best to finish up. I took Calc twice myself, Calc 1 and Calc 2, because I got C's the first time, but for engineers that wasn't going to get me into the school. I retook it, had a dyslexic professor who thought and I found out I got A's. Those replaced the C's and I was all good, but it did take me two times through. Okay, so that's my advice. Stick it out. Everything is a win. Even if you fail and you look at it, it's not a failure if you learn from it, right? And you move forward and keep going with things. I know it's sometimes a little painful, sometimes a lot of, yeah, I cried a lot, but hey, got over it. Next day comes. Okay, substitution. So today we're going back over, remember, we came up with this integration. If we see this sign, let's just put in here something not too bad, x to the third dx. What is x to the third in this context? What kind of a function is it? Not yet. It's the derivative. We will look for the antiderivative. Good, good. So we're looking, this is saying get me the antiderivative. What I'm giving you is the derivative. So this is a derivative of something. So remember, to find that antiderivative, we just did everything backwards. So instead of subtracting one, forward, you take the exponent down and multiply, and then subtract one. The other way, antiderivative, you add the one first. So instead of subtracting one, you're adding one first, and then you take that new and divide, not multiply. So we found that this would be x to the fourth over 4 plus a constant. Okay, and remember that constant was because when you take a derivative of a constant, it becomes 0, so it obliterates it, it erases it. We don't know, there could be some other number, so this is all the possible answers. So we're going to do this today, but what we're going to add to the mix, another, like trying to juggle the balls, so this is like 2 balls, we're going to add a third one, which is the chain rule. Okay, so this is, we're now going to be given a derivative that was obtained by the chain rule. So we're trying to go backwards on the chain rule. And so we'll start there. Okay, technique of substitution. So we're going to start with taking a derivative. So this is review, but we want to see the process again of what happens when we take the derivative using a chain rule so that we can go backwards to get what we started with. Okay? So, and I'm going to use the technique of substitution, which I sort of glossed over when we were doing the chain rule. I said just cover it up and say this is something to the 6th power, so let's take that outside derivative and the inside derivative. I'm going to be a little bit more formal this time, and I'm going to say what we're going to do is we can identify the inside of the function because it's inside parentheses generally. Sometimes it's up inside of an exponent. There's other ways to, or inside of a square root or something. It's inside something, right? So that inside part we're going to call u. So we take that inside part, it's going to be u. When we go to take the derivative, remember we would, so let me make the substitution now. This is u to the 6th power. So when we take its derivative, remember this is the forward operation. We bring the 6 down and we subtract 1. So this is taking a derivative, not integrating. But because of the chain rule, we also have to take the derivative of u, so that there's u prime here. Okay. So what this looks like, this becomes, the derivative is going to be 6 u to the 5th power times the derivative of u. So up here, maybe let's go ahead and take the derivative of u, right? Derivative of u is going to be 2x. And so if we followed sort of this way of finding, using the chain rule to find a derivative, we now back substitute, because right, our answer is in terms of u, but that's something we made up. The question given us was with an x, so we replace u with what it's equal to. So this becomes 6 x squared plus 1 to the 5th power times 2u, or sorry, 2x, right? Because the derivative of u is 2x. And you might leave this as a final answer. 2 times 6 is 12, x squared plus 1 to the 5th power. Okay, so you see how that taking a derivative with a chain rule sort of, we just put a u in there for the inside stuff, and it makes it simpler to work with. And then once we've got everything simplified, we plug everything back in, and there's our final answer. Okay, we're going to use that same technique as we go backwards, because today what they're going to give us is they'll give us this answer and ask us to get the antiderivative, ask us to integrate, ask us to go back, and we should end up with this. If we go back, if we do it all right. We're going to take a fresh example, but very close to this, and see how this will work. Okay, so all we're doing is now, in this section, we're going backwards. And this is what I mean is sometimes if the chain rule didn't really click or strongly click with you, it will maybe in this process of going backwards, sometimes it'll click better. Sometimes you don't really understand how to get to grandma's house until you came back from grandma's house. Oh, that's what, yeah, take these to, or going back and forth, back and forth. Okay, now I know how to get to grandma's house. We always used to go from Portland to Seattle, and when I was a kid, just riding in the car, sometimes we think, oh, Dad, you should turn here. But, after about, I don't know, a couple hundred times of visiting grandma, we finally all got it. Okay, so I tried to go through, and I took out, there's a couple pages that I used to have in here, but it was a lot of formulation, and it probably was more, in fact, it kind of confused me at times more than anything. So I'm going to try to kind of go with one system through. So here we are. We're starting with a derivative. How do we know this is a derivative? There's a couple things in there. The little squiggly here, so this integration sign tells us we're asked to integrate it, and we always know that whatever in there is a derivative. Also, this dx is indication that what's in there is a derivative. So those two things tell us, hey, there's a derivative in here, find the antiderivative. Find what the function was that this came from. And the cool part about all of this is at the end, once we have our answer, we can take its derivative, and we need to get back to what we started with. So there's a way to check. And I'm going to encourage you to do that check, because you'll see as we go through there's opportunities to make small errors along the way, and if you'll check, you'll catch your errors because, oh, it wasn't quite right. Oh, I forgot this little part. I forgot this negative or something. You'll be able to do it. So let's go ahead and go through here. So first thing we look for, and then after we're done with this, I've got some step-by-step process, but we're going to think through the process, do it, and then we'll formalize it. So first step is to find what is the inside function. What thing is inside? What do you think? X squared plus 1. It's in the parentheses. So it's kind of, yeah, that's how we kind of are. And in the homework, I think the first 3 or 4 are set up like this, where the inside is inside parentheses. So this is what we want to make our u. U equals x squared plus 1. Just like in that last one, very similar. So that's the first step. Find something, call it the inside part, set it equal to u. That's going to simplify it. Second step, which we kind of didn't do last time, is to take its derivative. So we're kind of think of implicit derivatives. So notice how we kind of tie all this stuff in. We're going to take the derivative of both sides of u equals x squared. So what is the derivative of u? It's 1 du. We're going to not, du dt if we were doing it with respect to time and stuff, but we're kind of just, don't worry about that part. Just call it the derivative of u. So it's 1 times the derivative of u. On the right-hand side, we have x squared. Its derivative is 2x to the first. The derivative of plus 1 of 1 is 0, so that disappears. And again, what did we do? We took the derivative of x, so we'll put a dx there. Now, I do it a little differently than the textbook because they were confused by, it was confusing. Anyway, their explanation. Mine works the same as they did. They might be more technically correct, but who cares about technical correctness? I care more about just getting it correct, right? And that sort of understanding a way that works. And then what we do, so notice, when we go to substitute, we've got dx, so we're going to substitute for dx, but Right now, we don't have dx by itself, so we want to get dx by itself. The other thing we're going to substitute for is we're going to substitute for the thing that we're going to call u, so we're going to replace this with u. So that's all set to go, but we need to know just what is dx equal to, so we divide both sides by 2x, and so we get that dx equals du over 2x. Okay, so we're going to make this as our substitution. Okay, so that's the first two steps. Find something to call u. It's going to be the stuff that's inside the function. Second step is take the derivative of both sides using sort of implicit derivatives, so we get du equals something times dx. And then now the next step is to rewrite what we were given with our substitutions. Now we didn't do anything with 4x, so we just leave it there. We're going to write it. U squared plus 1, well, we gave it a new name. We're calling that u, and it's to the 6th power. And then dx has a new name. It's now du over 2u. So I'm going to write this as du. And I'm going to emphasize the 2x is actually down here in the basement. We didn't know we had a basement, but we always have a basement because everything is over 1, right? So this whole thing is over 2x. You see what's going to happen here with that x? Because you're looking at that initially when you put that 4x and then you've got a u, we've got two different variables. And we haven't talked about that because we can't do anything with it. We can't integrate that. We need one variable, and we're going to get that to happen. So next we simplify. We've got an x in the top and an x in the bottom, so those cancel. X divided by x is 1. We have a 4 divided by 2, so we can carry that out. 4 divided by 2 is 2. And actually I'll put it out front because that's just a constant multiplier. I can move it out front. And so now what does this integral look like? Well, the 2's out front because we multiply by 2. We get u to the 6th power du. What could be more beautiful, right? This is a simple integration. This is almost like a standard thing where all we have to do now is add 1 to the exponent, divide by that new exponent, and we've got the integral. Okay, so let's kind of do that. And again, I write it on here just to kind of show my work, so I'm going to add that and then divide by it. And so this is going to give me 2 u to the 7th all divided by 7. Don't forget plus a constant. So we just integrated it. And that's the cool part, is if we do the substitution right, the integration is going to look very similar. It's going to look very easy because it's really just sort of like a standard thing. Okay, it doesn't have all this other stuff going on. Now the last step, back substitution is what I call it, because they didn't give us u, we made up u, so whatever u is, we plug that in. So we're going to call this 2x squared plus 1 to the 7th over 7 plus a constant. Okay. And now we are done. And we're going to do a check, just because that's, again, I told you we should. I should have probably given myself more room, but what we're going to do now is use the chain rule to take this derivative to see if we get back to where we started. And you could kind of do this mentally if you can, or whatever you need to do. So the check, 7 comes, so when I take a derivative, the 7 comes down, so I get 2 times 7 x squared plus 1. I subtract 1 from the exponent, which gives me a 6. I have a 7. Oh, look at these 7s are going to cancel. And then I've got to take the derivative of the inside, right? So I'm not doing all the formal process, but I know I need to take the derivative, and the derivative of x squared is 2x. I multiply by that derivative. Whoa, look at this. 2x times 2 happens to be 4x. X squared plus 1 to the 6th power. That's exactly what we had, and we took its derivative, so we could even put that dx if you want, but our function that we came up, our antiderivative, if we take its derivative, we got back to where we started with. So these things go back for, we checked. It worked. Does that make sense? And again, I encourage you to do both. It's one of those things, if you'll do it if it's easy, right? If it makes sense to you. I mean, I would. But the people who really need to do it is when it's difficult. If you're struggling with this a bit, you need to keep working with it. It will become easier the more you do it. But if you skip it and just stop with this, let me just plug it in and see if the WebAssign says it's correct. And you might do that a few times, but also remember, that's the nice thing about this, is we can check our answers by doing this. You get to the test, if it's a multiple choice, you could just take the derivative of each of the answers and see which one matches. So there's a way to check. Okay, there's a way to go back and forth. So here's the textbook kind of walking us through the same thing we just solved. Yes, they substituted u is going to be x squared plus 1. That's what they did. They took the derivatives. Notice they do it a little different. I just go directly to this. Well, not directly. What I did is I did du equals 2x dx, and then I divide by 2x. If you do du dx, you got to do this. There's actually two steps in between there to get the dx. So I just say, when I take the derivative of u, I'm going to put du. When I take the derivative of x, I'm going to put dx. And it works with the integration. So I do a little bit different than the textbook. It's not that they're wrong. It's just that they're complicated. Why be more complicated than you? So yeah, look at, they're doing this weird thing here, and you got to... I can't even explain it, right? It's too much. So then they go through, they make the substitution, and notice the 4x divides, the 2x divides into the 4x. We had this part. The x is canceled and simplified, so this is just the nicely printed one. So you can read everything. We do this is what we got, right? We did a back substitution, and we got that. And then we even did the check. I don't think they do a check, but these are the steps that we went through, right? First thing is look at it and identify the inside of the function. And what we're going to do is I've got some samples from the homework, and we're going to look at several of them. And at the very end of class, we're actually going to look through all the homework problems, and we're just going to at least identify which part do we make u. Sometimes the homework, they give us a hint. Make this part u, because that's the key part. If you when you're doing this, sometimes if you make the wrong part u, it's not going to work out. It gets really bad. So, and you just kind of learn, oh, it's getting real messy. Maybe I should try something else. But we'll try to get you so that this first one's a little more successful as you go through. Then after you find your u, you define something, something equals u, you take the derivative of both sides. So like I did, is you get du equals something dx, right? And that something is the derivative of whatever you had. Then we solve dx for du. So we take this something, divide it. So basically you end up with du divided by something. And that something is the derivative of that part. Then we make the substitution into the integration. Some things are going to cancel out, and then we integrate some simpler thing, just sort of u to a power or something, and then we back substitute. I forgot that here. Simplify, then integrate, and then 5, what I call back substitute. So put the x stuff that's in there. It'll look more complicated. Those are the steps. We'll follow each of these. We're going to do a few more examples, some with exponentials, some that turn into logarithms, but we'll see how this all works out just fine. So we look at this. We've got an x squared in the numerator. We've got this in the denominator. What does your gut tell you is the inside function? 1 plus x cubed. Yeah. The stuff inside the parentheses. So always look for parentheses or grouping. sometimes they're not there. Now 1.9 is a number, right? It's the exponent. And when we did derivatives, we typically would move those up and make them negative. So we're actually going to do that same thing. So I'm just going to rewrite this as x squared 1 plus x cubed to the 1.9, the negative 1.9 dx. Now the other thing I want you to see is once you identify that inside, you can also take a little extra step. X cubed is inside here. If you took the derivative of the inside, are you going to get an x squared? Yes. So what you kind of see with all of these types of problems, with these substitution problems, is the inside, the derivative of the inside is out there outside the parentheses. Because it has to be because of the chain rule. So you say, okay, I've got the right pieces, because if I take this derivative, I get x squared, something x squared at least. So we identified that u should be 1 plus x to the third, because that's inside. We take its derivative. Derivative of u equals, derivative of 1 is 0. Oh, I wanted to emphasize that in grading the exam so far, both classes, it wasn't extreme, but there was enough that so there was a problem that something was equal to 12, and you were supposed to take the derivative, implicit derivative, something. Anyway, there was a number that when you took the derivative of 12, you've left it as 12. Derivative of 12, derivative of any number is 0, right? Derivative of any number is 0. So I want to emphasize that because a few of you, didn't get that part. Derivative of x to the third is going to be 3x squared. And this is what I mean. We've got an x squared there. We got an x squared there. dx. What's the next step? Solve for dx. Right? Get dx by itself. So we get that dx, I'll switch sides, is going to be du divided by 3x squared. And you'll see if you use this method, it always works that way, is that once you take the derivative, du is always divided by that stuff on the outside. And remember, that's really just the chain rule. We're taking the derivative of the inside stuff. So from the chain rule, that will help it all cancel out. So I guess this was step 2. Step 3, let's go ahead and make our substitutions. We'll do it in this version. So we've got the square root of x squared. That's just nothing happened to it. 1 plus x cubed, we're now calling that u. So this becomes u to the negative 1.9 power. dx is all of this stuff. So that becomes du. And then let's make the basement, the bottom of the fraction, because everything is over 1. And what's down here is 3x squared. Okay. So we've done the major part of the substitution. This is the substitute. We've changed names and substituted just to make it simpler. And what we do now is simplify a little bit. So here's an x squared divided by x squared. That'll be 1. This is 1/3. So when I kind of go to simplify things, I'm going to put the 1/3 out front because it's just going to be a constant multiplier. I'll integrate and then multiply by 1/3. Okay. Do you see that should be a 1/3? Because sometimes we get moving. Sometimes it's the algebra parts of all of this. This is in a fractions kind of can cause some problems. And then we have u to the minus 1.9 du. So notice we've got something very simple to integrate. And it's a exponent. It's a negative exponent, but that's okay. We can follow our steps. Remember, we add 1 to the exponent first, and then we divide by the new exponent. Negative 1.9 plus 1 is going to be negative 0.9, right? And so what we get is we get 1/3 times negative 0.9, right, in the denominator, and in the numerator we have u to the negative 0.9. plus a constant. And what do we do now? Well, we back substitute. So u is something we made up, so we put this back to where it's supposed to be. So our final answer, we can simplify this a little bit. 3 times negative 0.9 is going to be, 3 times 9 is 27, so that should be negative 2.7. U, no, we want to get rid of u. We want to back substitute for u. U is 1 plus x to the third raised to the negative 0.9 power. And again, you could put that down and make it positive 0.9, but I think WebAssign would accept either one. We could just leave it like this. This is, oh, plus the constant, right? As long as you just sort of recognize it's there sometimes, so. Okay, so that's its integration. Now 1 over negative 2.7 is kind of a weird number. You're mixing a fraction with a decimal, so you could plug that in your calculator, take 1 divided by negative 2.7 and change it to a decimal. That's fine. Yes?
Sorry, can you just clarify where you got third from?
Where I got what?
Where you got 1 over 3 from?
Sure. It came really right here, right? Right here. So there's a 3 in the denominator, nothing. So there's, and remember, there's always an invisible 1, so it's kind of that 1/3. But those are the things I mean that usually what will get us is what's supposed to be the simple fraction algebra stuff, because those are, it's not simple. And we're not as proficient as, you know, the only reason I become proficient is because I get paid to do math every day and for the last 25 years. So, and I do it a lot. So I've gotten better. But when I was taking classes, you take one math class and you take, what, probably 4 other classes and something else. It's hard to remember all the little pieces.
Wouldn't it all have to, I'm probably wrong, but wouldn't it all have to be over negative 2.7?
Sure. Yeah, so when we do this, this is actually up in the numerator. So you could write it that way. You could also, because it's a negative exponent, put it back downstairs and have it as a positive exponent. So multiple ways of writing. Yes. Yeah, so it would be okay to have your final answer as 1 over negative 2.7, 1 plus x to the third to the positive 0.9 plus a constant. So there's a way, or you could put the 1 plus x to the third to the negative 9 up in the numerator multiple ways. And that's the thing with math is there's multiple ways we can do it. Someone I was working with was saying, why do we use so many different, and like we use different names for the same thing? So yes.
Since, because you have 1/3 and you're multiplying it by u raised to the negative 0.9 over negative 0.9, right?
Mm-hmm.
Wouldn't it be altogether 1 plus x third raised to the negative 9
Mm-hmm.
over?
Yeah, we could do that.
2.7?
Sure.
Or you would do that also? Okay.
Yeah, so if I have this as negative 0.9, it's in the numerator, and then so that's over negative 2.7. So that's a correct way to write it. This is a correct way to write it, and this is also a correct way. I can move it back down and make it a positive 0.9. So yes, multiple ways. But when we look at them, they seem different. They are, I mean, yeah.
Thank you.
Sure. And again, even if this is a multiple choice type answer, we don't know who created the exam, what version they're going to use in that multiple choice. So we might get to a right answer, but then we don't see it listed, and we've got to say, okay, what algebra did they do to make it different? And sometimes WebAssign does that, right? They make you simplify in some weird way. They don't accept the other one. Okay. Questions before we move forward? Okay, because again, if you want to understand each step as clearly as you can. However, again, clarity doesn't come initially from watching somebody. It's once you work through it a little bit and go through it. Okay. Now, the other thing is this dx is up here, but it's actually It's actually a big dx on the line down here. It's not up in the exponent. Okay, so we'll just kind of get that out there. What's the inside function here? Good. So I'm actually going to put a parentheses. It's the whole exponent. The whole exponent. So when we have exponentials, generally, because remember how we took its derivative, using the chain rule, e to something was its own derivative, and then we would take the derivative of the exponent. So the exponent is the inside stuff. So we're going to say u equals 9x squared minus 7. Good. So when we have exponentials, that's what we're going to want to do. And also, basically, I copied these directly from the homework. It was spring semester, so they might be slightly different, but there'll be something similar enough here. First step, identify u, set it equal. Second step, take the derivative of both sides. So then derivative of u is 1 du. Derivative of 9x squared, 2 times 9 is 18. 2 minus 1 is 1, so that's x to the 1 power. Derivative of negative 7 is 0. So that's plus 0. We don't write it. And then what did we do? We took the derivative of x. Next step, solve for x, or dx, right? So move the 18x over, and I'll kind of write that out. So we divide both sides by 18x. And so we get that dx equals to du over 18x. And I remember learning this stuff, and I didn't, it took me this was like 3 weeks down the road before I figured out how to do it the right way, because I was trying to use the way the book used, and it didn't make any sense. And I kept getting it wrong because there was a step I was missing in there. So that's when I came up with this. I said, this is much simpler, but it's not how the book taught me. I had to kind of reteach myself. So what's our next step? Well, we've got everything ready to go. We put our pieces together. We rewrite this as the integral. We just leave the x there. It's a little uncomfortable, but that's all we can do. We've got a substitution for 9x minus 7. 9x minus 7 is now, we're just going to call that u. And dx now is going to be du over 18. So I'll write that as du. And again, 18 is in the denominator of everything. And it's looking more simple than at least when we started, right? So, but I can go a little bit further. I see an x in the top and an x in the bottom. So in fractions, x divided by x is 1. This 18, well, it's just down there in the denominator. So I'm going to rewrite that as 1 over 18, because 18 is in the denominator, 1's in the top. It's a number, constant multiplier. I take it out. What's left? EU to the, or du. So, and remember, that's indicating that this is the derivative of e to the u. What is the integral of e to the u? Because now we integrate, right? It's just e to the u. So that's, again, it's so easy, but it's difficult because you go, really? Yeah, it's its own derivative, it's its own integral. So once we got the substitution, that's all good. This 1 over 18 tags along for the ride, and we have a plus a constant. Last step, we made up u, so let's put what u actually is. We do the back substitution part. So we put this back in for u, and our final answer is going to be, again, you could, let me do this. 18's in the denominator. E is to the 9x squared minus 7 power, plus some constant over here. And again, if you go through and take its derivative, you'll see you'll get e to the 9x squared plus 7, because it's its own derivative. And then when you take the derivative of 9x squared plus 7, you get 18x squared. The 18s will cancel, but the, oh, no, you get not you get 18x, right? X to the first power, and that's what will take us right back to what we started with. Okay, so when you get your answer, when you get the antiderivative, take its derivative, you'll get back to what you started with. Yes?
So the du turns into the plus c.
Kind of. The whole thing is once we integrate the du, someone asked this yesterday, it sort of just evaporates because once we've taken its derivative or have gotten the antiderivative, the derivative part is gone. Yeah, this is the way I like to think of it. In a sense, the c is part of it too, because that's an unknown constant and we don't know, so we just say it could be an infinite number of possibilities that it could have had that we just don't know because we've got the derivative. And once you take the derivative, the constant becomes zero, so you don't know what that constant was unless you've got some additional information. Okay? So just kind of, again, this will hopefully help because it is more complicated, more complex, but in going through this, you'll kind of follow these sort of step by step. So if any struggles you've had with the chain rule will become clearer. We won't be testing you directly on the chain rule in test 3, just we'll be doing this stuff, this substitution. But remember, the final brings back everything, so that will help you with test 1 and 2. By the way, I said in the other class, over the time I will make a solution video for both test 1 and test 2, so that and I'll just work through it so you can kind of figure out what part you want to watch, but then you could take your exam, anything you missed or anything you got, whatever you want to look at, you can compare how I did it and maybe how you did it, and hopefully learn for each of those, because again, the final may have similar type questions. It won't have the exact same questions, but they'll be similar, right? So I want to make that there. Application. So this one's going to be a little different, but it's important to take a look at this one. Now, there's an indication here that we have that what they're giving us, that this function is a derivative function. What is, and it's a simple little thing, a small little thing, what tells us that this is a derivative? Little word. Per, yeah. That tells us gallons per year. That is a rate, right? That's a fraction. The per is saying, so this is a rate. A rate is a derivative. A derivative is a rate. Okay, so that's the key part. Look for it. Whenever you see something per miles per hour, whatever, that's a rate. So when you see that word per, you know you have a derivative. Okay, one of the indicators. So T is time in years since the start of 2000. And then the question that's being asked is find an expression for the total amount of bottled spring water for pets sold since the start of 2000. The full question's not here, but so this is one where if we know the rate, which that is a derivative, if we get back, remember I said if you get back to the function before the derivative, that gives us a value, an amount. And so that's what we're getting when we integrate. We'll be able to get the amount of bottled water sold over a period of time. And I guess it's bottled water for your pet. So lucky pets, right? So what we really want to do is we want to integrate, because we don't want a rate, we want an amount. So we're going to integrate 3,000 e to the 0.5 t divided by 3 plus e to the 0.5 t dt. Now, looking at that expression, what jumps out to you as a possibility for the u to substitute? What is the inside of the function? What's that? 0.5t, because it's the exponent. We could try that. It would end up still being very messy. I'll just tell you that because Those are ones what I would try before, because that's what we've done so far. The thing is that we got an e to the 0.5t in the top and one in the bottom. And so we'd have an e to the u over e to the u. And it just, if we tried it, which we, sometimes it's good to go through it, but I don't, we'll spend maybe 5 or 10 minutes and we say, oh, that didn't work. So we won't do that. It's not going to work nicely. Do you see another sort of grouping of stuff?
Can we move the denominator up to the top and then count that as the inside?
You can, and that's exactly sort of what we want to do, is we want to see the denominator is a grouping. If you move it to the top, it'll be to the -1 power. And what I want you to think, because remember, we always got to be thinking backwards and forwards, that when we take the derivative of natural log of x, when we take its derivative, remember we got 1 over x. Or we got x to the -1 power, right? Either way. Or. So you could use it as -1 if you like. I see it more as being a 1 over x, so I'm going to leave it in the denominator. So this is one, when it's to the 1 power, we leave it there. Had it been something other than 1, so had it been something in the denominator to the -2 power, -3, whatever, we would then move it to the top. But since it's not to a power, it's really to the first power. And again, you could move it to the top, but when you see this happening, when you use the whole denominator, when you integrate, you're going to get a natural log. Okay? So let's just, I'll leave it down there because, again, we could do it either way, but this is 3 plus e to the 0.5t. And that's in the homework. There'll be ones like this where you might, again, that's the first, when I was trying this, that's the first thing I do. Okay, the exponent, let me try that. It doesn't work. It doesn't get you anywhere. And you're frustrated and you spend a half an hour working on it because you think, I got to make this work. It's not. So in the homework, when they get ones like that, they will typically give you a hint and say, use this as your u, and then it'll all come easier. And then, so once we have identified a potential for u, we take the derivative of both sides. Derivative of 3 is 0. What's the derivative of e to the 0.5t? E to the 0.5t, and then using the chain rule, we've got to take the derivative of the exponent. Derivative of 0.5t is 0.5, right? So we came up here, 0.5t, we took its derivative, that's going to be 0.5, 0.5. Okay, so that comes up front, and then we've got dt. So again, you got practice with this. So, and again, if you forgot about that 0.5, you'll get close, but you'll be a little bit off. But those are the types of things I would miss up to. But eventually, you get this practice. You get the practice with the chain rule too. And then what do? We solve for dt. We want dt by itself. So we divide everything by 0.5, e to the 0.5t. 0.5 e to the 0.5t. That cancels. So we're going to put this in, and we're going to put u in for this statement over here. So let me change colors. We're going to integrate. We still have this 3,000 e to the 0.5t. And actually, we could put the dt up there. This stuff in the bottom, 3 plus e to the 0.5t, we're going to call that u. And then when we substitute for dt, dt is now du 0.5 e to the 0.5t. And this is sort of one of the hallmarks that you know that your substitution is going well, is that there's going to be a cancellation between the variables. You're only going to have u. You're not going to have a u and a t, or a u and an x, because the second variable cancels out, and that's what's going to happen with this one. That wouldn't happen if we put in the other one. So e to the 0.5, e to the 0.5t, those cancel. That's 1. 3,000 divided by 0.5. That's 6,000, right? Because it's take the reciprocal 2 times 3,000. So we end up with 6,000 integral of du over u. Now, if you remember it this way, you can say, okay, that just integrates to natural log of u. If you don't remember it, you could move it up and have that u to the minus 1. Again, you just have to remember, because if you have u to the minus 1 and you add 1, you get 0, and nothing happens. But this is that 1 we have to remember. We end up with 6,000. When we integrate something over u, that's going to be the natural log of u. Usually they'll put absolute values, so you may need to do that for your answers in WebAssign. The reason they do that is because you can't put negatives into logarithms. You can't also put your zeros, so it's just a way of doing it. We won't have you take the derivative of absolute functions, absolute value functions, again, plus a constant, and then the last step, do the back substitution. So this is 6,000 natural log of 3 plus e to the 0.5t plus a constant, and that's our function. That's our integration. Okay, we're just about there. This is the last example we'll take a look at. This takes it another step, which we'll walk through that. But since this rate, they started to measure in 2000, what we can assume is what we do is we make year 2000 t equals 0, right? So at t equals 0, we started counting, so the output s of 0 should be 0, because at the beginning we haven't counted anything, right? So that's what they use, and with that piece of knowledge, we can figure out what c is supposed to be. Now I'm going to let the textbook go through it instead of work, because it's kind of like in our homework, we don't have any problem that has us do this, but I just want to show you we can figure out once we get to this stage. So here's what the textbook starts with. They do the integration, which we've done that part. We're going to integrate, and they tell us what to make u, that whole bottom. And they solve for dt, same as we did. They do the substitution, they do the canceling, you get 3,000 over 0.5, which is 6,000, and then they go that it's natural log of u, they use that. And then it says, because S of t represents the total amount of bottled spring water for pets sold since time t, we have that the beginning was 0, and so they are able to they plug in 0 has to be equal to 0. They're able to do the arithmetic here and solve for c, and they get that c is equal to this number, which is actually, if you plug that in your calculator, is 8,318. So we figured out what the constant is, and now we can use this function to figure out after 5 years how much water has been sold. We would plug in 5 there. Again, we're not going to do an example that has this level, but I want you to get familiar with the u substitution, so start in on the earlier ones. There are a few applied problems, but not quite as rigorous as this one. There's also some shortcuts which are embedded into the homework. I don't find them helpful at the beginning. They might, after you've done this a few times, you'll naturally see, oh, there's like this kind of problem is always going to be like this. So sometimes you're able to not have to go through the u substitution. You'll be able to get there by using the shortcuts. But to look at them right now, I think is overkill, and I'll show them to you because they're in WebAssign. So let's go into WebAssign, and we're going to talk about how to set each one up, each of the problems, at least what the U is. Um, So 13.2, we're just going to view the homework. And this is what I mean, the very first one, there's this little link here. If you click on that, it will show you all the shortcut. And I had these as slides, but I took them out because I said you have access to them when you're ready. Take a look, and if it makes sense to me, it's just like so much, like even gives me a headache to look at them right now. But after you do it a few times, you'll see, oh yeah, if it looks like this, it's going to integrate easier. And some of you, I just don't use shortcuts all that much myself, but I know some of you may want to. And the textbook, oh shoot, I got out of it. The textbook will have you using it as well. Or they'll indicate that you should use it, but you could also just use substitution. It's a little bit longer, but a little bit easier to go through. So this first one, what should we make U? Yeah, the inside, 5x minus 4. Let's see. Yeah, and everybody's will be a little different. So yeah, basically, so we end up, what we'll look at is whatever's inside those parentheses, right? This one, same thing. So you're going to make the inside stuff here be your U. This one, it is the whole exponent. So again, we kind of go back and forth, and sometimes we do want to make that exponent. So this one, because it's not in a fraction. This one, and again, they give us a hint, because should we just make x, or should we make 1 over 8 and it make the whole exponent, u, but they give us the hint. So follow their hints, and you'll see if you use that one, it all will work out just nicely. This one, again, you've got, something in front, so I see 2 sets of parentheses. What should we make? Well, again, they give you the hint that it's the whole exponent, so it's 8x plus 8 squared. Use that, and you'll be able to get everything will work out nice. Again, if you take the engineering version of this, they don't give you all the hints, and a lot of times you'll spend half your time working through something and you'll find just that it didn't work. Maybe that teaches you something, but it's a hard way to learn. So it's nice that they give us some hints, because it's, sometimes we just get frustrated and we stop, don't we? At least I do sometimes. The inside of a square root, and so what we're going to, when we go to do this, we're going to want to rewrite this as negative 5x plus 6 to the 1/2 power, right? Just like when we took derivatives, because we're going to add 1 to the exponent. So just rewrite square roots as something squared, and it, okay, yeah, it's the stuff inside the square root. It's nothing new, it's just a fractional exponent. Same thing here, another square root, so everything inside the square root is what we're going to call u, and then we're going to rewrite it as to the 1/2 power. Okay. This one, again, stuff inside here, it's to the 3rd power. You'll see that x will take care of itself. It's kind of like what we did. This one, again, we might think, oh, make the whole denominator. Well, no, this one, just the inside here, and then rewrite that, right, as a negative 1.7. So, and that'll make the integration all that much easier. But the u part is just the inside, and that negative 1.7 is actually the outside part of the function. This one, again, there's no parentheses, so notice they start breaking it down, but it will be the whole exponent. And again, you'll do these again and again, and you'll get good at spotting where these are. This one's nice, they've got parentheses, but again, you could say Should it be x plus 7 or should it be this thing? And this negative should be included. So it's the whole, when we're doing the exponential, typically it will be the whole exponent. Whatever's in that exponent, that becomes u. Okay. This is going to be that sort of weird one where the whole denominator is what is going to be u. But you can yes?
Why is it the denominator, not the numerator?
Because of this thing of that the natural log of u, when we take its derivative, we're going to get 1 over u times the derivative of u. So the derivative of u gets up in the numerator. Good question. And what you can see here is if you look at that numerator, each of the exponents is 1 less than the ones in the denominator. It is the derivative of the denominator. So the denominator is what we want to start, what we want to say is the inside function. The numerator is the derivative of the inside function. So on these ones, you'll see they're always set up that way. Okay. And again, these are special case deals. If this numerator was missing, like if this was just x to the 7th, we couldn't do this. It needs to have all of this stuff in here. So we're doing some specialized stuff that doesn't necessarily naturally occur. But to be able to do this, the numerator has to basically be some kind of a derivative of the denominator. Good question. Same thing here. We make the denominator, oops, I don't want to cross it out. We make the denominator RU. Okay, and you'll see it will integrate into natural log of u. These get a little trickier. I'm not sure I even remember this one. You've got two things. I think I told the other class to use 8x. It may work. You might, if it doesn't work, try natural log of x. So they're going to give you a few where you can do it, but there is a multiple choice one here, so you can kind of see which one works. Same thing with this one. You get x natural log of x. What should we make? And you can always remember there's an ebook. They'll have some examples, and they probably have something similar to this. But again, should we make the whole denominator, or that's a product rule? That's good. Maybe if we just make like natural log of x, I think you're going to have better success here. And so up here, my suggestion maybe try u equals natural log of x first, and I think you'll be in better shape. Yeah, I think those will work out. Again, here we're told that this is the slope of a tangent line, so that's a derivative. When we go to integrate, again, use the exponent itself as your u, and you'll see that, yeah, x squared, if you take its derivative, it's going to match up with that. This one, use this inside and then write it as something to the negative 2 power, move it up. This one, so you're going to have your inside the parentheses. I think that'll all work. And give these a try. The last ones are a little bit more complicated, but again, try to get at least through the first maybe 4 or 5. Get some practice with that process and work on the rest. And if you got questions, let me know, and we'll keep moving forward. All right. Thank you. Happy Halloween. Stay safe.